Hey, welcome back to ClearSpot. What if I told you that AI-powered predictive maintenance systems can achieve 94.3% accuracy in anomaly detection and 98.2% precision in fault localization, while reducing unplanned downtime by 47% and generating annual savings of $425,000 for a single solar installation? And what if I told you that predictive maintenance typically helps homeowners generate 15 to 25% more energy compared to systems without monitoring, and that machine learning algorithms can predict and prevent 89% of potential failures, leading to estimated cost savings of 2.3 million euros over 3 years? Today, we're diving deep into the revolutionary world of solar panel health monitoring and predictive maintenance, technology that's transforming solar panels from passive energy generators into intelligent, self-diagnosing power systems. Over the next 20 minutes, I'm going to take you through a comprehensive journey exploring how a 75-megawatt solar installation in Arizona integrated 12,000 distributed sensors with sophisticated AI and machine learning infrastructure, achieving a 64% increase in mean time between failures and reducing maintenance response time from 72 to 4 hours. We'll examine real-world case studies where the University of California solar farm showed a 27% increase in energy yield after implementing AI-driven predictive maintenance protocols, and reveal the cutting-edge techniques that are enabling operators to detect micro-cracks and potential hotspots before they could impact performance, resulting in a 15% reduction in downtime. This isn't just about fixing problems after they occur. This is about creating solar systems that heal themselves, predict their own maintenance needs, and optimize their performance automatically for decades of peak operation. The solar industry is undergoing a fundamental transformation in how we approach maintenance and system health. Traditional maintenance of solar photovoltaic plants is generally done using preventative or corrective methods, meaning inspections and replacement of components at regular intervals or in response to a sudden fault. This reactive approach is not only expensive but often results in significant energy losses and system downtime. Predictive maintenance really revolutionizes solar photovoltaic system performance by detecting potential failures before they even occur, which helps reduce downtime. The transformation here is honestly pretty dramatic. Instead of just waiting around for components to fail or, performing unnecessary scheduled maintenance, predictive maintenance uses advanced sensors and artificial intelligence algorithms to monitor system health continuously and predict when maintenance will actually be needed. Modern predictive maintenance systems, well, they rely on these really sophisticated sensor networks and artificial intelligence. IoT-enabled sensors give us the capability to collect real-time data on important parameters like solar irradiance, temperature, voltage, and current. This allows for comprehensive monitoring of system performance as well as environmental conditions. These sensors are working around the clock, measuring everything from panel efficiency to weather conditions, and they automatically transmit data to centralized monitoring systems. AI algorithms, including both machine learning and deep learning techniques, make it possible to automate fault detection, predictive maintenance, and anomaly identification based on all the data that's collected. What makes this technology especially powerful is its ability to learn from historical patterns and spot those subtle changes that might indicate developing problems long before they would ever become visible through traditional monitoring methods. Let me show you some verified data that demonstrates the incredible impact of predictive maintenance. Solar Tech Solutions' 75-megawatt solar installation in Arizona implemented an AI-powered predictive maintenance system over a period of 18 months, integrating 12,000 distributed sensors with, sophisticated AI and machine learning infrastructure. The results were extraordinary across multiple dimensions. The system achieved 94.3% accuracy in anomaly detection and 98.2% precision in fault localization, with a 47% reduction in unplanned downtime, generating annual savings of $425,000. But the operational improvements were equally impressive. A 64% increase in mean time between failures, reduction in maintenance response time from 72 to 4 hours, and a 3.2% improvement in panel efficiency. These aren't just marginal improvements, these are transformational changes that fundamentally alter the economics of solar operations. Academic research is validating the incredible potential of predictive maintenance in solar applications. A notable case study from the University of California solar farm showed a 27% increase in energy yield after implementing AI-driven predictive maintenance protocols. The system's capabilities went far beyond simple monitoring. Smart sensors detected microcracks and potential hotspots before they could impact performance, resulting in a 15% reduction in downtime. This level of early detection represents a quantum leap in solar system management. Traditional visual inspections might miss microcracks that are invisible to the naked eye but can, significantly impact long-term performance. The system continuously improved as it processed more data, becoming better at predicting panel degradation, optimizing cleaning schedules, and spotting hardware issues before they escalated. The success extends beyond academic installations to real commercial applications. A large-scale commercial installation in Arizona achieved a 23% boost in power output by combining dynamic load management with real-time weather data integration. The implementation included automated cleaning schedules and dynamic load management that added an extra 2.4 kilowatt-hours per panel in daily energy production. What's particularly impressive about this case study is the comprehensive approach to optimization. The system didn't just monitor for faults. It actively optimized performance based on real-time conditions, weather patterns, and historical data to maximize energy production throughout the day and across seasons. The benefits of predictive maintenance have been validated across multiple geographic regions and installation types. In Europe, a collaborative research project across multiple solar facilities documented an average efficiency improvement of 31% through the integration of machine learning algorithms for performance optimization. The system successfully predicted and prevented 89% of potential failures, leading to an estimated cost saving of €2.3 million over 3 years. This multi-site validation is particularly important because it really demonstrates that predictive maintenance benefits aren't limited to specific climates, installation types, or even geographic regions. The technology works across a wide range of conditions and scales, from residential rooftop systems all the way up to utility-scale solar farms. And honestly, the benefits extend to residential applications as well. By keeping solar panels operating at their best, predictive maintenance typically helps homeowners generate somewhere between 15 to 25% more energy compared to systems without monitoring. This increased efficiency translates directly into greater energy savings and a faster return on solar investments. Many homeowners actually report spending up to 70% less on repairs after implementing predictive maintenance systems. The technology really pays for itself within the first year through prevented damage and maintained efficiency, and then it just continues to provide value throughout the system's operational life. Modern predictive maintenance systems, deploy these really sophisticated sensor networks that monitor multiple critical parameters all at once. IoT sensors, which are installed on solar panels and throughout entire solar farms, communicate important parameters like voltage, power output, tilt angle, temperature, humidity, and honestly a lot more, back to the cloud for analysis. These sensors, they provide unprecedented visibility into system health and performance. Various sensors are deployed to measure critical parameters such as solar irradiance, temperature, voltage, and current output of solar panels. These sensors are connected to microcontrollers or IoT devices that are capable of collecting, processing, and transmitting data wirelessly. The collected data is then sent to centralized servers or cloud platforms for analysis and storage, where sophisticated algorithms work to analyze patterns and trends. One of the most powerful diagnostic tools in modern predictive maintenance is, without a doubt, thermal imaging analysis. Predictive maintenance makes use of infrared thermography and drones to inspect solar panels. Thermographic cameras are able to detect overheating or other safety risks by identifying vulnerable areas, which helps prevent deterioration. Drones equipped with these cameras can monitor large solar arrays, enabling a continuous and efficient assessment process. This technology can detect problems that are completely invisible to visual inspection. AI algorithms identify and localize hotspots on solar panels, which indicate areas of excessive heat that can reduce efficiency and potentially lead to damage if left unchecked. What used to require weeks of manual inspection can now be accomplished in a single day with far greater accuracy and detail. Inverters represent one of the most critical and vulnerable components in solar systems. Inverters are the leading cause of solar panel failures. Machine learning algorithms monitor inverter health, comparing performance against expected patterns. Unusual behavior triggers alerts for operators, enabling swift intervention to prevent equipment damage. Machine learning algorithms are being deployed to analyze inverter error logs and operational data, enabling the prediction and diagnosis of faults. This capability allows operators to optimize resource allocation by dispatching maintenance crews only when necessary, rather than following rigid preventive maintenance schedules. The sophistication of modern AI systems in solar monitoring is truly remarkable. AI-powered performance analysis works like a smart health monitor, continuously collecting and interpreting data to spot potential issues before they become problems. These intelligent systems analyze patterns in temperature, energy usage, and equipment performance, learning what's normal for specific setups and alerting when something seems off. So, AI doesn't just track thresholds, it actually learns from historical patterns, real-time signals, and even environmental conditions to recognize those subtle signs of underperformance. As the system gathers more and more data, it becomes increasingly accurate at predicting when maintenance will be needed. This really takes the guesswork out of system care and helps operators make well-informed decisions about upkeep and repairs. Modern predictive maintenance systems can detect an incredible range of issues, with a level of precision that really surpasses traditional inspection methods. AI algorithms, for example, can analyze vast datasets, everything from aerial thermography photos to sensor readings from solar modules, and pick up on small anomalies that might signal potential issues before they escalate. This comprehensive approach ensures that no potential problem goes undetected. IoT systems have this amazing ability to predict potential failures or maintenance needs by analyzing historical data and identifying patterns that might indicate impending issues. These systems can actually distinguish between normal performance variations, which are often caused by environmental factors, and real equipment problems that require intervention. The early warning capabilities of modern systems are, honestly, just unprecedented. Smart sensors and real-time monitoring act like an early warning system, continuously monitoring crucial components and collecting real-time data about performance, temperature, and electrical output. These sensors work around the clock, measuring everything from panel efficiency to weather conditions, detecting subtle changes in performance that might indicate dust accumulation, aging components, or developing electrical issues. The data is automatically transmitted to a central monitoring station where sophisticated software analyzes patterns and trends. What makes this technology particularly valuable is its user-friendly interface. Operators can access real-time information about system health through simple mobile apps or web dashboards, with notifications sent when maintenance is needed. The power of modern predictive maintenance lies in its ability to recognize patterns that indicate future problems. AI uses machine learning algorithms to analyze patterns from data collected over time, such as temperature fluctuations, voltage drops, or abnormal energy production. Based on this data, AI can predict potential failures in components like inverters or battery storage systems before they cause a system failure. For instance, AI might flag a trend where a certain panel is consistently producing less energy than others. Rather than waiting for it to break down entirely, the system can alert technicians to perform maintenance. This proactive approach prevents costly repairs and minimizes downtime, which is, crucial for large-scale solar installations. Advanced systems don't just detect problems, they can automatically respond to optimize performance. AI can even suggest optimizations, such as adjusting the angle of solar panels to better align with changing seasonal sunlight, or addressing shading issues that impact performance. If a sensor detects that a particular panel is underperforming due to cloud cover, the AI can adjust the angle of the entire array or redistribute energy between panels, ensuring efficiency even in changing environmental conditions. Real-time data collected by IoT sensors is sent to a central cloud-based platform, where AI tools process the information and automatically adjust system parameters to optimize performance. This level of automation transforms solar installations from passive energy generators into intelligent, self-optimizing power systems. The economic benefits of predictive maintenance really extend far beyond just simple operational efficiency improvements. The integration of predictive maintenance solutions has demonstrated substantial improvements in system performance, with studies showing up to 30% reduction in maintenance costs and a 25% increase in system availability. When these improvements are applied across entire solar portfolios, the financial impact becomes, truly transformational. One of the most significant advantages of AI and IoT in solar systems is, honestly, the cost savings they bring. Predictive maintenance helps avoid expensive emergency repairs by identifying issues early. The SolarTech Solutions installation generated annual savings of $425,000 through reduced downtime and optimized maintenance scheduling, demonstrating the substantial return on investment possible with advanced monitoring systems. The operational benefits translate directly to improved financial performance. Maintenance costs can drop by 25 to 35%, with 70% fewer breakdowns. Facilities report up to 25% increased productivity and 20 to 25% extended equipment lifespan. These improvements, really compound over the life of the system, creating substantial long-term value. Early detection of loose connections can really prevent damage to expensive inverters, while spotting partial shading issues can help maintain optimal energy production. These technologies usually pay for themselves within the first year through prevented damage and maintained efficiency, and then, they just keep providing value throughout the system's operational life. The environmental impact of predictive maintenance is, honestly, equally significant. The SolarTech Solutions system contributed to a reduction of 1,960 metric tons of CO2 emissions annually and conserved 1.2 million gallons of water per year. These environmental benefits really show how predictive maintenance contributes to broader sustainability goals, all while improving economic performance. By keeping the system performing at its peak and extending equipment lifespan, predictive maintenance actually reduces the need for premature component replacement and minimizes waste. This sustainability aspect becomes more and more important as solar installations scale globally and environmental impact becomes a critical consideration. Predictive maintenance creates long-term value through multiple mechanisms. The system's environmental impact is equally significant, contributing to a reduction of 1,960 metric tons of CO2 emissions annually, demonstrating how operational improvements translate to environmental benefits. The continued evolution of machine learning algorithms and sensor technologies will further refine predictive maintenance capabilities. As these technologies mature and become more accessible, they will continue to drive innovation in the solar sector, fostering greater adoption of solar energy solutions and contributing to a more sustainable energy future. The monitoring systems themselves continuously improve as they process more data, creating compounding value over time. Successful implementation of predictive maintenance requires a comprehensive approach that integrates multiple technologies and strategies. By leveraging the synergy between IoT and AI, solar panel monitoring systems can achieve higher levels of efficiency, reliability, and autonomy, ultimately leading to improved energy production, reduced maintenance costs, and enhanced system resilience. So, the implementation process typically involves deploying various sensors throughout the installation, establishing reliable communication networks, implementing cloud-based data processing platforms, and of course, training operators to use the new systems effectively. The key here is really finding the right balance between monitoring comprehensiveness and system complexity, all while ensuring cost-effectiveness. Modern predictive maintenance systems, honestly, are designed for scalability and adaptability. The system's scalability allows for easy integration of additional sensors and devices as monitoring needs evolve, making it adaptable to growing photovoltaic installations while still maintaining reliable data collection and transmission. Different installation types definitely require different approaches. Residential systems, for example, benefit from simplified monitoring focused on key performance indicators, while utility-scale installations require comprehensive monitoring of thousands of components. The technology has to be adaptable to these diverse requirements, all while maintaining cost-effectiveness. The future of predictive maintenance in solar applications is being shaped by emerging technologies. The development of more sophisticated diagnostic tools and automated response systems will enable solar installations to operate with greater autonomy and reliability. Advanced technologies such as drone-based thermal imaging, AI-driven soiling detection, machine learning algorithms for inverter diagnostics, and AI-based weather pattern analysis are changing traditional approaches to maintenance. Looking ahead, the continued evolution of machine learning algorithms and sensor technologies will further refine predictive maintenance capabilities. Integration with smart grid technologies, blockchain for transparent maintenance records, and 5G connectivity for real-time monitoring will continue to enhance the value proposition of predictive maintenance systems. The widespread adoption of predictive maintenance is transforming the entire solar industry. For stakeholders in the solar industry, embracing predictive maintenance technologies is no longer optional, but essential for maintaining competitive advantage. The future of solar PV systems will be characterized by smart, self-monitoring installations that can anticipate and prevent failures before they occur, ultimately leading to more reliable and cost-effective renewable energy generation. As solar energy plays an increasingly vital role in the global transition to renewable energy sources, predictive maintenance becomes essential for ensuring the reliability and efficiency of these critical energy systems. The technology is moving from experimental implementations to standard practice across the industry. Solar panel health monitoring through predictive maintenance has evolved from experimental technology to essential infrastructure for modern solar operations. AI-powered predictive maintenance systems achieving 94.3% accuracy in anomaly detection and 98.2% precision in fault localization, 27% increases in energy yield, and 47% reductions in unplanned downtime represent a fundamental transformation of how we manage solar energy systems. The evidence is overwhelming. Predictive maintenance typically helps homeowners generate 15 to 25% more energy, reduces maintenance costs by up to 30%, while increasing system availability by 25%, and prevents 89% of potential failures while generating cost savings of 2.3 million euros over 3 years. These benefits apply across all scales, from residential rooftops to utility-scale solar farms. Whether you're a homeowner protecting your solar investment, a commercial facility manager optimizing energy costs, or a utility operator managing massive solar portfolios, predictive maintenance technology offers transformative benefits that justify immediate implementation. The integration of predictive maintenance solutions has demonstrated substantial improvements in system performance, and for stakeholders in the solar industry, embracing predictive maintenance technologies is no longer optional but essential for maintaining competitive advantage. We're entering an era where solar panels are no longer passive energy generators but intelligent, self-monitoring systems that predict their own maintenance needs and optimize their performance automatically. The future of solar PV systems will be characterized by smart, self-monitoring installations that can anticipate and prevent failures before they occur, ultimately leading to more reliable and cost-effective renewable energy generation. Your solar panels should be working as intelligently as the technology that created them. The question isn't whether to implement predictive maintenance, it's how quickly you can begin realizing the benefits of intelligent solar energy management that maximizes every ray of sunlight and every dollar of your investment for decades to come. Like, share, and subscribe for more solar insights. ClearSpot, smart device, smarter decisions.